I'm sorry, ничего не... I can't see, I can't hear anything.
Can you hear me now?
Okay.
Yes, yes.
Okay, perfect.
Okay.
So we begin. Our speaker is Vladimir Rubtsov, and he will tell us about Källén function and around. Volodya, you're welcome. Это нужно, чтобы вот там, не знаю, это куда угодно.
Сюда.
Держи. Ты равно себя уже изгадил.
Ну, хорошо. Жена.
Так, а это куда-нибудь.
Угу. Так хорошо? Слышно?
Да. Вот так.
Вот так. Ага. Отлично. Так. Значит, I will speak English, yes? I should speak English.
Yes, you speak English.
Yes. So I want to, first of all, of course, I'm very grateful to be here and to be invited for this seminar, which is a kind of my native seminar, continuation of my native seminar, and I'm always very happy. Thanks a lot, Alex. Thanks a lot, Joseph. Today, I will try to give a kind of survey, colloquial talk about the subject which I was excited very much in the last couple of years, maybe. And I make a choice for this survey presentation, very special function, which is called Källén function. I'm grateful to Alec and Joseph who corrected my initial pronunciation, because in Europe I had only Källén function, and then I understood that being Swedish citizen, Gunnar Källén should be pronounced Källén, and in Russian translation it was always Källén. So my hero today is Källén function. I want to insist that it is a wonderful and very important function. Maybe not so much important like exponential, but I will try even argue that they are maybe not very close cousin with exponential function, and this function is quite beautiful, and as exponential function, beauty of Källén function in its simplicity, and it is a kind of ubiquitous object. It is almost everywhere present. So I want to start with definition and elementary, very elementary, just on the level of high school. Oh no! Oh no! Oh, nothing special. Ладно. Окей. Виктор Матвеевич. Миша, напишите, пожалуйста, Виктор Матвеевич, что я стою у доски. So I'm sorry for this interruption. So I will start with elementary properties. Виктор Матвеевич, я сейчас стою у доски. So definitions. So what the Källén function is, as I told you, it is the function which everybody, almost nobody knows, and almost everybody knows. So this function is the following. It's usually standard notation for this function is lambda. It's came from physicists. First, this function appeared in the textbook partial kinematic by two Finnish physicists, particle kinematic, published in 1971, US Curie universities. And they, this presentation based on the original papers of Gunnar Källén, and he used this notation. It is a function of three arguments, x, y, z, and it is the sum of squares x, y, z minus 2 times x, y, 2 times x, z, 2 times y, z. So this function, it is a polynomial. I will use basically C or R polynomials in my talk. And the basic properties of this function are the following. First, it is from its very simple form, absolutely clear that it is sigma 3 invariant. Second, it is quadratic. In each variables. So considering like a function of x, it's quadratic function with coefficients in y and z, and symmetrically. And of course, it is it satisfies three beautiful quadratic equation: z square minus 2 times x plus y, z plus x minus y square equal to 0, and so on. X square minus 2 times z plus y, etc. I want to just to draw your attention that this equation will be very important because
What is the first sum?
this one, z square. Z square. It's, sorry.
And where is our function?
This one.
This one what?
You can write this function as a quadratic square.
And why 0? Why 0?
I want to say that when I'm studying this function, zero of this function, the zero of this function will define in future so-called two-valued group, two-valued multiplicative law. In this case, it will be group law.
I don't understand.
What?
Who equals 0?
The function, this one. Osia. Look this function. Take z square. Take minus z times 2 times x plus 2 times y. Okay? What you have here? You have x square minus 2 times xy plus y square. This is exactly the same function. No?
You mean that?
I mean that you can write
You written this way.
this. Yes, it is important. It is important for definition of two-valued group law,
Okay.
and you can write it in
Okay.
each variable. Okay. I'm starting with very elementary things. The next property of this function is that if you consider this like a quadratic function, for example, in Z, you are able to compute the discriminant. And the discriminant is splitted. It is the simplest example of very, very rich class of interesting polynomials for which you are able to compute the discriminants or a discriminants in sense of Gelfand and Kapranov-Zelevinsky, and all these discriminants will be factorized or splitted. The importance of this splitted property is that they split it in the same function of other variables. You compute this, and you have function, linear function in x and linear function in y. If you compute x discriminant, you obtain this, etc. And of course, it is not for nothing. It means that also you can write this function. It's like a discriminant of some other polynomial. If you want.
Если равно нулю закрыть, то все понятно. Это функция, которую вы написали, есть лямбда, как вы ее определили.
Да. Okay. The condition. Condition equal to 0. It will be important condition. This condition. This red triangle. This condition lambda equal to 0. Дойдем. Okay. So what I want to say that this function can be written in its own. It's a discriminant. It's a discriminant of z minus x minus y minus 4y is z. And this is the discriminant in variable t of polynomial, and polynomial in t is.
Sorry, you mean x, y.
You
mean xy. Yes. 4xy. Minus 4xy.
Minus 4xy. Thank you, Miss. So z t square plus x plus y minus z t plus y. It's also trivial. You can write also in y t square and x t square. You will obtain the same polynomial.
Z or x?
Yes.
Condition.
What?
T square.
T square should be z, I suppose. Z, yes, and this y.
Then the determinant will be.
Huh?
Then the determinant will be different from.
What?
Потому что в нем мультигрин-z, а вот написано.
Сравнение.
YZ?
У тебя там 4YX, а здесь будет 4ZY.
And so what?
Or you can change the signs.
No. Stop. If you take the discriminant, what you have? This guy, You want this?
It's not what I want, but
Yes, yes, yes. Oh, for this guy, it is yes. Thank you. But you can write it in any. It's always symmetric, so it doesn't matter. Of course, you should be careful. Yes, the most well, all these trivial properties. The most non-trivial maybe if you take so-called Kummer lift. Two Kummer lift. It's a special Cremona transformation of P2, special quadratic, very simple Cremona for P2. So you have x, y, z, considering like homogeneous coordinates in P2. This Kummer lifts to u square, v square, w square. If you take this, then the Källén function, this Källén function of new variables u, v, and w, factorized. It's quartic. Which we will factorize in u plus v plus w, u plus v minus w, u minus v plus w, and minus u plus v plus w. And of course, you can also split it in the following. Being a function of x, y, z, from this you can easily split it in z minus square root of x plus y square root. This factorization is also has some sense for what
Z written in different ways is the same guy.
you mean.
You mean I mean Z?
Maybe sign appeared.
Well,
Maybe sign appeared in front.
no, I mean Z calligraphy.
Sorry. Yeah.
Yes.
Yes. Yes. It's a. It's like people who use left hand and right hand in both ways. Sometimes. So I'm ambidexter here. This very nice property, especially.
I mean, this is how the last formula relates to the previous one. Why did you need the previous formula?
In principle, I don't need, but
You do.
I don't need, but it is easy to. It is not maybe easy to go to this formula from the very beginning, but maybe not. Anyway, these two formulas, they are important in each own way. Why this formula is important, everybody can easily understand. If we consider this u, v, and w like lengths of sides of a triangle on the plane, non-trivial triangle, such that if you need for each pair of these three factors triangle inequality, then you have the area formula for this. I want to draw your attention that it is not a half perimeter, it's a full perimeter. So this lambda, u square, v square, w square, it is just 16s triangle in square. So if you have this triangle square, then this function gives you this.
А можно еще один вопрос задать?
Of course.
Ведь в Героне там P всегда скрытно. P по минус А, по минус Б, по минус С. Тут, чтобы вы P не назвали...
I told that if we suppose that this, for each of these three summands, triangle inequality should satisfy.
Я к тому, что там вот если вы что-то логически через героновское P,
Да,
то в формуле Герона оно все время...
да,
плюс.
конечно.
А тут
конечно.
один раз все переменные стоят с минусом.
Ну, да, но они в стороны, поэтому они все положительные. No, if I take this like sides, the only condition that this side should satisfy to, of course, if I suppose that u, v, and w are lengths, they should be positive, of course. So I don't care about this, but I'm caring about this. Okay? So that's the second. I wrote here, by the way, I forgot from the very beginning, I forgot said that what I'm telling today based mainly on two papers with Victor Buchstaber and Ilya Gayur. One paper will be published in Izvestia in January, and second paper I hope to finish during my visit. It is the second part of this first paper. Also, many inspiration and information from various papers of Victor Buchstaber since 1975, when he started to study formal and two-valued groups. And even in the last months, he published with his young co-author Misha, who is here, very interesting papers related to this subject. Unfortunately, I have no time today to speak about it, but maybe I will mention at the end what can be done in the generalization. Many things in generalization is even now done by Misha and Buchstaber in the last two preprints of October. And also this two physics paper and book, of course, I spent much more time to study what they wanted to do with this Källén function. Very brief remind about this factorization. This factorization comes, of course, from Fériet, from Alexandria, and I have a picture of this Greek mathematician. Fériet. Sometimes in Greek it is Fériet. In Russian tradition, even in English, we write Fériet from Alexandria. Of course, we know his name from school time because of this formula for triangle area. And that's why Källén function relates to this Fériet formula. And very recently from Petya Pushkar, I knew that also Heron was probably inventor of the first power machine. All my life I was sure that it was James Watt, but in fact it's Heron. And he...
Ну, это требует проверки. Это требует проверки.
The problem that he didn't use it for some profit. He just considered it like a toy. He made this steam machine like a toy, and he called it Okay, and now I want just to use this possibility to show that there are some other interesting formulas related to area and to Källén function. So I can rewrite this formula in multiplicative way, namely I can write that this is square root of P A B C, sorry, product ABC, where ABC, it is half of these factors. So A, it is a half of x plus y minus z, B, correspondingly, x minus y plus z, and C, minus x plus y plus z over 2. And P is usually half perimeter. Using this, it is not difficult to check very nice determinantal formula for this area, which also gives determinantal formula for our function. So S of my triangle equal to square root of 1 over 2 A plus B plus C times the 0 AB, A0 C, B C 0 symmetric determinant of A, B, and C, where A, B, and C expressed in terms of X, Y, Z like this. And from here, you can write the formula for X square, Y square, Z square, like X plus Y plus Z over 2 times the symmetric determinant X minus Y, X plus Y minus Z, X minus Y plus Z minus X plus Y plus Z, 0 X plus Y minus Z, 0 minus X plus Y plus Z, and also this X minus Y plus Z. It is not just my... what? No, it's in square, you see? And also 16 is inside of it. Yes, it may be a little bit in advance, not right now, because it is not related directly to my function. But I want to say that there is also a beautiful family of determinants which gives the area volumes for n simplexes. So it's so-called Källén-Menger determinants. This is a family of determinants for volume given. They give the volume of sigma n, and sigma n it's a simplex in R to n. How the determinants are constructed, and then let's consider vertices of my n simplex. So we have n plus 1 vertices. Then we can construct a matrix. It's a kind of Gramian Bij. This is a matrix times n plus 1 times n plus 1. And this matrix elements Bij, they are square of minus Vj Euclidean length. So it's lengths of edges between vertices with indices I and j. And then we construct matrix n plus 2 times n plus 2, framing my matrix B by 0 and units. And then this matrix is called Källén matrix Mn. Determinant M sub n, it is it's a theorem. You should check it by hand for n equal to 2, for n equal to 3. Even for n equal to 4, it is possible to do by hand. It's 2 times n factorial, n square times minus 1 to n plus 1, multiplying by volume of sigma n square. So the volume, square of volume of my n sigma gives this, is given by this determinant with this coefficient. So for n equal to 2, you have this easy formula, which involve my Källén function. Very nice formula. I think it deserves to be written. I will, because I want to save my time, I prepared also formula for tetrahedron volume in terms of this determinant, but I should stop here and go to the next story, because my talk isn't quite informal. The next story is the story of Källén and his function. Who is Källén? Gunnar Källén was a Swedish physicist. I would say now phenomenology physicist, but at that time they said theory in theory physics. He was born in 1926, and died in 968. So you see, he died very early, and the death was not natural. I will tell the story. He was very good and brilliant physicist. He submitted thesis in Lund University and started to work in theoretical physics in Lund University. And together with some other physicists, in 1952, he decided to organize a kind of Scandinavian nuclear physics centrum. And they organized this Scandinavian nuclear physics center, which they called CERN for future project of all European centrum. But this CERN in 1952 was in Copenhagen. And then when this centrum became really all European centrum, they moved to Geneva. But the institute which Källén and other people established now is called Niels Bohr Institute. So it's a very good example of Arnold theorem that Niels Bohr never was in origins of Niels Bohr Institute. Anyway, he worked in this place until 97, when CERN moved to Geneva, and he came back to Lund, and he was very respectful with other physicists, Gustafsson, who now there is a big price of Gustafsson's name, and even some people used this money. Anyway, from his youth, he wanted to be a pilot. And he, when he became famous and reasonably rich, he bought small plane and took lessons of driving this plane. And in 68, he took his plane with his family, with his wife and some other people, and he had a crash between Malmö and Copenhagen. It's a very short distance, maybe like between Medvedkovo and Kalushskaya. And in this short distance, this plane had a crash, and he was the only person who died. Other people survived. And his wife wrote a book about him. She was in this plane. So this was really a very interesting and beautiful person. I have a picture of him. Unfortunately, I can't show you. What he did in physics. In physics, he did two things which deserves to be mentioned. In fact, he made many other small things, but his biggest invention was so-called Källén lemon. Lemon, another very famous physics personage of this time. He was one of the creators of so-called formal field theory. This formal field theory was kind of mathematical answer to Bogolyubov. The same ideas, but Bogolyubov used divergent integrals, which he tried to regularize perturbatively. But Lemon, Simanchik, and Zimmerman, they tried to introduce some axioms, and using these axioms, they tried to completely avoid the using of divergent integrals, but it was not it was not possible. But at the end of 60s, it was very popular among mathematicians to study formal field theory. And when I was 50-year student, I attended seminar Brodsky and Naumov when I first knew this story. And the story is that there is a Källén-Lemon spectral representation. I don't want to go very far, but when you study the so-called casual green functions, it means that if you take a free particle without interaction, for free particle, if you neglect spin, then free particle behavior in cinematic completely defined by so-called four vector of momentum. Four momentum vector. Vector P. It's a vector in 3 times three comma one Minkowski space with indefinite metric, and this vector is the argument of so-called casual green function of propagator. Casual green function, it's mu spectral measure, and P, it's a four momentum vector. And this is the casual green function. It's a function of this type. You have P squared minus mu squared plus E epsilon. So it's a divergent function. It's a density. It's like in sense of Sakhotsky or something like this. And then if
P is
P is four vector.
and mu and epsilon.
Epsilon, it is just a number. This is also a kind of number which comes from Minkowski metric. And you have they proposed for this free particle this representation element dp. It is integral from 0 to infinity rho, which is density measure function, but whatever, and here it is d mu divided by this p squared minus mu squared plus e epsilon. So of course it is a kind of divergent integral, but it is what people call
understand completely. So how does this or do these formulas
relates
to our particle?
to
What is known about the particle?
I will go just to explain it, probably a little bit more detailed. From which this comes, from which situation this comes. This situation comes when you write up. Okay. From so-called Feynman diagram, let's suppose that we have interaction of electron, positron. As a result, annihilation of electron and positron, people draw like this photon gamma. And then, as a result of this, it is just example of such scattering. This photon split for two quarks, quark Q and quark Q bar. And then also sometimes people suppose that this Q bar quark gives birth to a heavy particle which is called gluon. I can't say that it's a quark. Q bar is anti-quark. And then this diagram gives birth to such kind of formulas and Källén function. This diagram, no. It is not understandable. It is just an illustration of in what situation people study this. What Källén function did, I will explain. This is understandable. So if we have a relativistic quantum mechanical description of particle kinematic, so we, as I told you, we should take for momentum. For momentum, it's a for vector. And also this for momentum satisfies is usually the relation with mass times for velocity. And for velocity, it is just usual velocity times gamma of u times u bar. So this is a four vector. This is a
What is
no, I'm sorry. So this in this quantum relativistic, you should take u. It is gamma times four vector c. C it's a the
light speed?
Light speed, yes, and this is a three-dimensional velocity. And gamma it is just a usual Lorentz coefficients. One minus v over c. V bar this.
Yes.
Yes, and then this is just m times gamma c v three-dimensional. This four-dimensional vector, it's like this. And physicists say that, okay, even from this relation between velocity and momentum with this coefficient, it is a central notion in special relativity that you have equivalence between energy and matter. And then this vector momentum can be defined not only by mass and velocity, but also by energy. divided by c, and three-dimensional momentum. And this is more or less energy matter equivalence. So if you write this in terms of energy, you can write the energy equal m gamma c squared, that everybody knows from at least maybe from last high school, Einstein special formula. P is equal to m gamma v sub bar. So these two equalities show the equivalence between matter and energy. And it means that we replace by this guy, by this m times this coefficient, the rest mass in classical relation mass, momentum, and velocity. Now we want to apply this consideration to interaction of two particles. Let we have two particles, A and B. And these two particles, they have energy and momentum in this description. So we have particle A momentum and particle A energy. And we have energy particle B and momentum particle B. So we have this data. Then we have total momentum of this interacted particle. Total momentum is given by product of these four vectors. S square equal to PA plus PB square equal to EA plus EB square minus scalar product. Sorry, PA plus PB minus, so like this. Let us also denote by MA and MB masses of this particle. And then this
What are these brackets?
scalar product in four-dimensional space.
But
In this indefinite.
I don't know. E is a number and P is a four vector. So how do you compute this product?
Sorry, it's my fault. Yes. So S, you're right. S square, it is the square of PA plus PB. PB, and then we can write it like
In Euclidean norm.
no, not Euclidean.
In Minkowski.
Minkowski, yes. And this is EA plus EB minus PA plus PB, but bars, like this. And then, okay, we have masses, MA square plus MB square minus 2 times PA times EB minus PA times minus PB, usual scalar product.
Верхняя строчка связана?
It's a square of four vectors.
Или это разные, маленькие и побольшие дальше?
No, PB without subscription.
P без это
It's-
четырехмерный, а это трехмерный кусок.
Мгм. And of course, I forgot that here in this formula, we should take c equal to 1. It means take the system where velocity equal to 1. Then we can play with this formula. What does it mean? It means that we should add some additional constraints. For example, we should suppose that our system where we consider our particles, it is a center mass system. In center mass system, sum of momentum equal to 0. It's like in usual mechanics. PA plus PB equal to 0. It's additional constraint.
Not underlined for dimensional P.
It seems that it's for 4. Or 4.
Ну и тоже фу.
Okay.
Yes. And when the two particles interact, then as a result of interaction appears new particle. And this particle is called target particle. This target particle has its momentum pt. And of course, this momentum pt depends on momentum of interacted particle. So it is just pta. It is a sum pta and ptb. The next simplification is that for one particle, this part of target momentum equal to 0. It's by hand. It's a constraint. And then energy of B of this target system particle also equal completely to initial mass B, our particle B. If we impose this condition, then, and it was the observation of Källén, then momentum of resulted momentum PA T computes by the formula square root of L S MA MB in square divided 2 times MB. And this is a famous Källén.
What is S?
This.
Ah.
So this is the first Källén function first appearance of Källén function. Well, this we can now. Then the physicists started to study this function, and I put in my presentation all formulas which I put in the first line: symmetry, factorization, and this presentation is a product of two factors with x, y, z. They put it here in this textbook. Of course, they considered it like an important object. Then the most beautiful application of Källén function in the context of two particle interaction was so-called line interaction of two quarks. So it is line interaction. You have interaction of two quarks, top quark and bottom quark. And as a result,
Sorry. And the second restriction with E and M is due to the unit velocity of
Yes.
of light. Yes.
Yes. And then that's what Källén himself computed. He considered an interaction of top and bottom quark, a quark. As a result, they obtained the W boson, heavy particle W boson. And then the parameters of Q top are momentum top, massa top, and energy top. And the same for bottom. P, B, MB, and EB. And the same, of course, for W. P, W, MW, and EW. And for this triple, Källén gives the following observation.
For boson.
Жалко, что стер.
Нет, я хотел поехидничать.
Это вы получите это.
А ты нам пришли?
Я вам пришлю.
Не повесил.
Мгм.
Мистер,
Что? Нет, тут я все...
можно переворачивать боковые доски.
Okay. So condition PB plus PW equal to 0. EB plus EW equal to M massa bottom T, massa top. This condition came from the observation of this MB square equal to EB square minus PB square, MW square equal to EW square minus PW square. And then for center mass, they have the formula M square W, this W boson, equal to MT square plus EB square minus 2 times MT EB. This I checked it, minus PB square. And from this, using these relations, you can obtain two expressions for EB and EW. The energy of bottom expressed in terms of square mass, MT square plus MB square, minus MW W square divided by 2 times MT, and EW equal to MT square plus MB square minus MB square and plus MW square. So it's divided by 2 times MT. Of course, you can recognize 2 of 4 factors if you replace these arguments of Källén function by this mass. And momentums W and bottom, they coincide from this. And they write Källén function of 3 mass B, T, and W. This was his main formulas for this reaction.
А нижние формулы для медиан треугольника напоминают. Это случайность?
Нет, не случайно. It's...
Well, I don't ask why such a restriction.
This restriction...
well, the only one. Yes, these two...
from center mass. This is from center mass. This from this constraints.
And all all the other formulas,
Yeah, all these formulas.
are they deduced from this restriction or they are additional?
No, from this restriction only.
They are deduced.
They deduced from this
Okay.
restriction, yes. And then what they studied zeros of Källén function when these momentum are zeros. And they called these values of masses, they called it threshold values.
How?
Threshold. Пороговый. Threshold.
Да.
Threshold. And these threshold values form a triangle. These threshold values are beautiful. M.
So we are in.
Let's just for simplicity, we will not write T, B, and W, and we'll write M square, M2 square, M3 square.
Вы там на картинке просто потерли свои же M1 axis, M2 axis.
M3.
Вот, на нижних углах.
This M3, M2 axis, M1 axis.
So
This-
we are in R3.
Yes,
In R3 with
with three numbers.
with coordinates M.
Yes,
Okay.
maybe we are in a affine part of P2.
Okay.
If you want, we can be in a affine part of P2. And these threshold values are the following: M1 square.
Actually, P2, yes.
Yeah, M1 square equal to M2 plus minus M3 square. And then by circle, M2 square equal M1.
Вообще отображение трехмерного на двухмерное, да? Оси-то 3. Оси 3, то есть это
Ну,
изображение
это-
трехмерного на двумерное.
Да. What these values are correspond to this internal triangle. And if you take any of these three relations, then you have the zeros of lambda.
Due to this idea.
Yes. That's what I wanted also to explain you, but probably I have no time today. I wanted to explain you also that the same conditions appeared when you compute branching points for algebraic curve covering for 3-point Gaden model.
Sorry.
3-point Gaden model. So it's Gaden chain in statistical physics. If you integrate it, you write it like LA pair, this. And L operator has special structures, three-band matrix. From three-bandness of this Gaden for 3 points, you can compute the condition when the algebraic spectral curve of Gaden model admit branching points. It is a square quadratic equation. And if you construct determinant of this equation, it is exactly Källén function. This is one of appearance absolutely unattended. Today, I wanted also to tell you the story of multivalued, two-valued groups and Källén function. Zeros of Källén function define a multiplicative law for two-valued group. But I think if you want, I can continue. If you don't interested in it.
Let's decide. I wouldn't like to make it too quick. Maybe. Well.
Because I need
Be honest. How much time do you need for multi-valued functions and all this stuff?
1 hour.
No. Then let's split, and you will proceed in December.
In December
Yes.
by this,
Yes.
of course. Okay.
Because all.
Because I also prepared a very interesting part about kernels and
Yeah, let's
and then I can add also
Yes,
relation.
okay. So
What I can tell you, as a
all
publicity.
all slots in October and November are occupied already.
I see.
Okay, so
For me, it's
we
also
proceed
it's
to-
better because next
Yeah, we
I
proceed.
have a talk tomorrow and I have 2 talks next
Okay.
week.
Let's stop here. Okay.
Natasha
Yeah.
Amborg and her student, they made a very beautiful computation of branching points for triggered n. And then they showed me, and I said, "Oh, I know this function."
Okay. Now we stop here. Thank you very much. Questions, remarks? Thanks. Okay, then we say goodbye and meet in a week in Zoom. Володь, спасибо. No, not in Zoom. No, we meet here.